Welcome everybody to the latest installment of Foundations of Science. This is a class on coral reefs. Like I said, unfortunately we won't be able to get to a coral reef this time around, but well, we'll see what we can do as we go on. I'd like to start off with this quote from the Oglala Sioux. It turns out apparently my family comes from a Sioux line. I'm not sure for Oglala, but we do come from a line of Sioux and Cherokee, but that's another story. I digress. Live your life like the water, lower than everything but stronger than the mountains. Water is really a truly remarkable substance, and honestly, it gets me thinking about what our place is in the universe. It really is one of those things that makes you wonder about how possible life is on other planets. And I suggest you have a close look and think about this when you're reading the Carl Sagan book, Cosmos, for the Common Curriculum, because really our position in the universe is truly extraordinary, that we actually have water available in all three phases. And that's going to be one of those things that's absolutely critical as we go forward and think about how coral reefs manage to survive and why they're such special ecosystems as we go on. As I mentioned just a minute ago, water exists in all three phases on the surface of the Earth: the liquid form, the gas form, and the solid form of course being ice. If we look at the other planets in our solar system, Mercury is just way too hot. I mean, it's just crazy hot. But it's also too cold on the dark side. on the front side facing the sun, the temperature on Mercury can be upwards of 420 degrees Celsius. Now on the dark side of Mercury, the temperature can be on the order of 173 degrees Celsius, in the other direction minus. So we're talking about a 500-600 degree swing in temperature here, which is ridiculous. But that 173 degrees minus 170 degrees Celsius is way too cold for life to survive because everything would be frozen, and the 427 degrees Celsius is way too hot because all the water would boil and evaporate. And we'll also talk about why water is one of those elements that's essential to life and why it's essential to life. We'll get that in the chemical place. What we focus on first in this section is actually the physical side of water, what it is about the physics of water that makes it particularly well suited for life, and especially life on Earth. Similarly to Mercury, Venus is also too hot. The average temperature on Venus is on the order of 162 degrees Celsius, again way over the boiling point of water at 100 degrees. Turns out there's a very thick atmosphere on Venus, which kind of insulates it, so it's a little bit warmer than it would otherwise be because of that insulation. However, what that extra insulation does is makes you feel like if you're standing on the surface of Venus, kind of average elevation, makes you feel like you'd be under 1,000 meters of water. So it's absolutely crushing pressures in this area on this planet. So, again, it's not very well suited for life. Curiously, also in our solar system, our other next door neighbor, Mars, has something that looks like, for all intents and purposes, there was water on the planet at one time. We're pretty sure there's not water on it right now, at least in its liquid form. There probably is some kind of water frozen just below the surface, but that's still being studied, and we'll talk a little bit more about that later. There's still potential for some kind of life on Mars, but as Carl Sagan also mentions in his book, to find out how that possibility could play out, it's actually quite complicated. So, let's keep thinking about that as we go forward, and definitely pay attention to that as you're reading in the Cosmos book. I won't go to the other planets in our solar system because they just get kind of increasingly less and less, more and more hostile, I should say, to life, except one of the moons of Saturn. Europa is the image we see here. This is actually, you look at it, it looks like ice flows on a river. I know that our Singaporean brethren may not have actually seen this, but in all intents and purposes, looks like there was a frozen surface with these big rafts of ice that would have been floating on the surface and broken apart at different times, and then the material in between solidified again. And there's actually other evidence to suggest that there is actually beneath this ice a liquid ocean. Not only a liquid ocean, but a liquid ocean of salt water. Really fascinating geophysics of how they found that. One of the Voyager missions, I believe it's Voyager 2, went by and it had a magnetometer on it. And it turns out as the spaceship flew past Mars, as it flew past Europa, it actually picked up a significant fluctuation in the magnetic field of the planet, which made us think that it's actually generating its own magnetic field. The only way it could do that is if you had some kind of conducting material that was moving around the planet. That conducting material, in this case, we believe is salt water. It couldn't be fresh water because fresh water is not a very good conductor. But it could be salt water underneath, and it had to be liquid salt water because it has to be able to shear. Ice, even saltwater ice, is a very poor conductor, so it wouldn't be enough to generate a magnetic field that the Voyager mission picked up. There's been some proposals to actually send some kind of crazy probe there to actually see if there's any evidence of life underneath the ice, but that's a very, very, very long way off. And then how that information would get back to us is yet another challenge that we'd have to face as we go forward. Coming back to Earth, one of the most remarkable properties of water, and this stuff just, it's pretty remarkable how the substance, it still blows me away. I'd almost say that it gives me religion, but you know, I'm a scientist, I'm not allowed to say that. This is an image of a desert, and on the desert you can see an image of this shimmering there, the heat shimmers and mirage. Everybody knows that deserts are wicked hot, and if you were walking on this barefoot, you'd be in really big trouble. The reason why that is that most materials have what they call a very low heat capacity. And if you consider the heat capacity being how much heat does it take to raise 1 gram of a substance 1 degree Celsius. Now, heat is not the same as temperature. Heat is actually the same as work, or it's a force that's moving something at a given distance. So if you think about heat as being something moving around, things moving around and actually banging off each other generates friction, and that movement can actually cause increases of temperature. So really, temperature increases are a measure of kinetic energy, not so much the amount of heat in something, even though they're kind of the same thing. So anyways, a substance like sand, like quartz sand, really doesn't take much heat applied, external energy from the sun in this case, to raise 1 gram of that stuff 1 degree Celsius. Water, on the other hand, takes a lot more. Here's a list of some kind of common substances with their heat capacity. Excuse me, you can tell from water it's actually got the highest heat capacity of almost any substance, normal substance, natural substance on Earth, on the order of 4 joules per gram per degree K, about the same idea as how much heat you add. So it's 4 times more. Oh, okay, let's say it's twice as much as what polyethylene, which is plastic or paraffin wax, which occurs naturally in oil deposits. It's easily 4 times that of oxygen, which of course there's a lot of in the atmosphere. It's twice that of. I'm sorry, it's about 4 times that of quartz, the main component of sand. The only thing that kind of comes close, which has people scratching their head, is ammonia. Ammonia has a very high heat capacity also at 4.7 joules per gram per degree K. So people think, well, if there's life out there, it doesn't necessarily have to be water-based. It could also have an ammonia base. Now, what does heat capacity have to do with life, you might ask? Think about it. If water had a very, very low heat capacity, if there are temperature swings on the planet, we would go between boiling and freezing. I mean, sometimes it does get really hot. If our bodies actually heated up as fast or cooled off as fast as it does in our environment, it would probably stress our cell linings and like too much to actually have life exist. Another one of the more remarkable physical features of water is what they call the latent heats of water. My dad used to always tell me, well, boy, your talent is kind of latent. It's hidden beneath the surface of, in this case, it would have been teenagerness. But of course, it came out, and I'm shining now. But the latent heat, or this hidden heat of fusion and vaporization that water has, is pretty interesting characteristic. So if you take ice and you apply heat to it, you increase the temperature increases. So you kind of apply a steady amount of heat to the system, and the molecules are starting to move around a little bit, and the temperature increases. Right when you get to 0 degrees, even though you're adding more heat to the system, the temperature doesn't increase until you add an additional 80 grams or 80 calories per gram of heat. And then after you add that additional heat, the temperature starts rising again, and it rises from 0 degrees all the way up to 100 degrees. Right when it hits 100 degrees Celsius, water's starting to boil and starting to form steam at this point. It flattens off again. This time, to actually get water vapor to form, you have to add an additional 540 calories before that temperature changes enough and the temperature starts going up again and as the water molecules are released and broken apart to form water vapor. What's going on in there? They're actually working on breaking hydrogen bonds, which we're going to talk about when we get into the chemistry section. But this idea of latent heat, how those heats are hidden, is absolutely critical also to life on Earth. And it goes beyond what happens in any individual organism to how the planet actually operates on a planetary scale. You look at something like clouds. I think most of us realize that clouds are made up of largely water vapor. And when it has that water vapor, or actually vaporized or gas phase water in it, it has all that latent heat in it. And we'll talk a little bit more about this when we talk about weather, but when that gaseous form of water goes back into liquid form, it has to actually release all that heat. When it releases that heat, interesting things happen. Have you ever noticed that sometimes during rainstorms, you'll find that right before it rains or even during the rain, the wind picks up? Well, that's actually the phase change going between the gas phase to liquid phase of water, releasing that latent heat. That heat has to go somewhere, so it goes from keeping the water molecules separated to actually moving air molecules around and generating wind. It's really a remarkable system. Similarly, it's also responsible for distributing heat over the planet. We have a lot of our heat concentrated at the poles, at the equator. But then we have these large weather systems that move heat by way of clouds from the equator out to the poles. And that heat keeps the planet a relatively constant temperature. You might say it's a little bit cooler at the North Pole or the South Pole than it is here in Singapore, but I think you get the idea. If it wasn't for that circulation pattern, if we didn't have water, we'd have a situation that's more like Mercury, where we could have probably not a 600 degrees Celsius range in temperatures, but something a lot more than it is right now. So in our next lecture, we're going to talk a little bit more about the chemistry and the hydrogen bonds associated with water, and then once we have that sort of situated out, we'll go into weather systems. Thanks for paying attention, and we'll see you next time.